Flow is a natural phenomenon. No, you need not force something to flow. In fact, you cannot. What you can do is you can make a potential difference. Flow takes place automatically. Flow takes place automatically. If there is a pressure difference, flow takes place. The fluid flow takes place. Let it be air or gas or liquid or anything. If there is a temperature difference, heat flow takes place. There is a voltage difference, that's a potential difference. Current flow takes place. So flow is a natural phenomenon, and you don't have to do anything. Also, from measurement point of view, definition of flow is if there exists a energy difference or potential difference, the flow takes place. And the very formal definition of flow is the continuous deformation of the fluid when subject to shear stress. You know what is meant by shear stress, isn't it? Something which you apply does, and that continuously goes from one layer to another layer. In the form of layer, it just keep on sliding. That we call it as flow. Okay. Even in the pipe or channel, when the water is flowing, actually, if you use a lot of flow visualization techniques and go deeper into the analysis, you will understand one layer is sliding over the other layer. So it is because of the shear stress, the liquid or the fluid layers are simply sliding one over the other. So it is a continuous deformation of the fluid when shear stress is applied upon. Of course, for continuous deformation, you need to apply stress. It is not tensile, it is not compressive, it is shear stress. When you apply shear stress, it continuously deforms and flows. That process technically we define it as flow. Again, from measurement point of view, the term flow is very vague term. Now, we mean many things by flow. So, we have to be very specific by flow. What is that? What characteristics of flow that we are interested in? Like, if I'm saying I'm measuring temperature, it makes sense because I know what I'm measuring. If I say, sorry, huh? Yeah. If I am saying I am measuring flow, there is a confusion. What is that you are measuring? So there is something called volumetric flow rate that we normally call it as discharge, and there is also something called mass flow rate. Okay, and also we talk about velocity of flow. So flow, when there is a phenomenon, how much of liquid is flowing is one aspect of it, but what velocity is another aspect of it. So you should always tell what is that you are measuring, specifically when you are talking about flow measurement. Okay? From measurement point, of course, volumetric flow rate is how much volume of fluid per unit time that you are that is flowing through the pipe. If you measure that, is volumetric flow rate. Mass flow rate is how much mass of fluid is flowing in the given period of time. Is mass flow. Okay. And we have three devices. One is venturimeter, other one is rotometer, and third one is what is that? What is the third device? The heating element, pyrometer. Sorry, anemometer. Pyrometer and not meter. Anemometer. Okay. So these three devices only there in this semester. So that's very simple. Just a matter of child play. Maybe after a weekend, it's like a warm-up class. So you're going to find you don't have to stretch yourself. So this you might have seen maybe used as part of your fluid mechanics lab. Here you have a converging section, that's entrance section. It's a small throat section, and then there is a diverging section. Here about 21 degrees is the inclination. Here about 7 to 15 varies from application to application. Okay. Now our purpose is to find out what is the amount of fluid that is flowing through that particular pipe. So what we do is we purposely introduce pressure difference and measure the pressure difference. What is that we do? How do we create pressure difference? There is a converging section, throat section, diverging section. From here till here is venturimeter. Okay. That's a single device, and you you have one pressure tapping here, that's upstream pressure. Here it is in the middle, the throat. It is not downstream. Downstream is generally here. For Venturi, we say it is downstream in the common terminology, but this is in the throat. Exactly in the throat we will take the second pressure reading. And this is actually the upstream pressure. Before the section starts converging, you take the pressure. So when you take this pressure difference, reduce the, basically what we wanted to do is, we wanted to create a pressure difference. Okay. And that pressure difference will be high if the flow rate is high. It will be low if the flow rate is low. That's the idea. Okay. So people initially started with orifice meter. What is meant by orifice meter? You simply take a plate, put a hole, that becomes orifice. Right? Simply fit it in the middle of the pipe, that's orifice meter. Correct now? You heard fluid mechanics you people study? You might have heard about all this. Orifice meter, nozzle meter, Venturi meter. But you people are staring at me as if you are listening for the first time. Okay, so you simply take a plate, round plate, put a hole in it, that becomes orifice meter. And any reduced cross section, sudden reduced cross section, there will be a pressure difference. And you can measure upstream and downstream pressure. You can calculate the discharge velocity, whatever you want. But the problem is, because of the measurement, the flow gets disturbed too much. Because of, for the purpose of measurement, we reduce the cross section area. The flow gets disturbed too much. What is this effect is called? Loading effect. This effect is called loading effect. Loading effect is high in case of orifice meter. Then what is that? Nozzle meter. What is nozzle meter? How does nozzle will look like? Nozzle boys. Oh, first our sir will speak, we will simply come and say, huh? That inertia sets up, isn't it? What is meant by nozzle? Yeah? Yeah, a tube that is converging. A tube whose cross section is keep on reducing and goes to a lower value. Isn't it? If the cross section reduces, you call that section of the pipe as nozzle, simple. Okay. So people used nozzle for flow measurement because anyway you wanted to reduce the cross section. If you suddenly reduce, like orifice meter, the pressure loss is too heavy that we are not able to recover it back beyond recovery. So there is a pressure loss. We don't want to lose pressure, especially the pipe, whether it is a fluid transport system, whether it is a fluid power system. In both, pressure is very important phenomena as far as fluid is concerned. In most applications, not in all applications, most of the applications, pressure we wanted to retain because that is power directly given by the motor through pump. So we don't want to lose the pressure. So as much as possible we would like to recover the pressure, we don't want to lose it. So orifice meter, they said no, this is no good device for better measurement because loading effect is very high. You can measure, but loading effect is very high. Okay. Also, in the fluid mechanics, you might have studied different aspects of it. Coefficient of discharge is 0.5, 0.6 for this. For nozzle, it will be 0.7 to 0.8, and for orifice, it is 0.8 to 0.9. Some ranges that you might have studied. Okay, that all tells how much of pressure that you will be losing in the process of sudden cross section area reduction. Okay. Now, nozzle is only this portion of it. Don't worry about this throat, don't worry about divergent section. Only this, up to the entrance section alone. You take, that becomes nozzle. You connect it to another pipe, that becomes nozzle. The area is not suddenly reduced, gradually reduced, fine. Reduced to a smaller cross section area and then it is left. Then there is a bigger cross section pipe that comes in front of the pipe. So simply the liquid is poured in the form of a jet, and there will be some reverse flow forming eddies, and there are again a lot of pressure losses that we could not recover most of the pressure. Even it is better than the plate, orifice plate, but no, it is still there are a lot of pressure losses people want to improve on. Then what they did, they reduced cross section, and if you want to recover the pressure, don't want much loading effect, then they want a diverging section. So initially what they did, there is a converging section and there is a diverging section. So if the cross section is gradually decreasing due to skin effect and other effects, the fluid will keep on touching that outer surface and then slowly enlarge. So there is no eddy formation. So liquid fills the pipe and then goes. That is what is expected. And then the pressure will be recovered fully. But what happened? Because the cross section is reduced, like a jet, the pipe comes here. Even here and here, there are a lot of eddies that is getting formed. They said no, the eddies are there. So again, the eddies means pressure loss, the energy loss. Unnecessary bubbles and this form, energy is lost. You don't want that to be lost. So then they introduced for streamlining, we reduce the cross section. We don't want that jet to form and then go and fall there. So they made a smaller cross section as a throat section. The same reduced cross section they extended for some more time, then slowly diverging section. They introduced this to avoid the jet effect. Then throat came into the picture. So now there is no jet action. That means the pipe water all comes together, goes through the throat, and then slowly diverges. Okay. So there is no jet effect in that throat section because of introduction of throat section. Then the device, our purpose is to reduce the, to develop a pressure difference by disturbing the flow, and for the purpose of measurement. At the same time, we don't want to lose pressure because we are doing measurement. Okay. So our purpose is to develop a differential pressure. Here there is a pressure with which the water or the fluid is coming. Here there is a reduced cross section, definitely there will be a change in pressure. That difference is directly proportional to flow that we know. For that, they reduced the cross section area, but they wanted to regain the same pressure, at least 90%, 95% close to what the pressure that we had. So for that they introduced this throat section and a little more distance, and then there is a diverging section, and the section continues from there as a pipe. So as a device, the Venturi meter took the shape because of these reasons. And of course, you might have learned the expression for velocity, and velocity times area is discharge. So velocity is what is that? CD into square root of d1 by d2 d2 square. You might have learned the expression. What is the expression for discharge? Fluid mechanics. Yeah. Not studied. You studied this or not? Studied, right? So you relate the whatever the diameters of the pipes, the coefficient of discharge, and the pressure difference P1 minus P2 the whole square root of P1 plus P2 square root of that into CD, all that you substitute, you get what is discharge from this Because these are all specifications. Suppose you are planning to buy a Venturi meter, these are all the items that you will ask for. So I'm not going to talk. This basically is characteristics of instruments that we have discussed in the first two classes. The head losses is less, only about 10%. 10% is actually high, but compared to orifice meter and nozzle meter, this is less. That's why it is less. Very widely used flow measurement, and the coefficient of discharge is 0.9 and above. It can be used even in very larger pipes like irrigation or petroleum transportation from one country to another country, such a big country also, how much of liquid is flowing, that you will be able to understand. More space is occupied and very costly because normally it is all done using casting. Or of course nowadays for smaller pipes you get plastic or Venturi meters. But bigger ones are all casting, so normally it is big cost. Okay. Any questions on Venturi meter? Venturi? You might have learned all this, right? least you are familiar with the device. Okay. Rotometer is another device. You have a conical pipe, our scale, that is all, with a float. With a float. The principle that is involved there is when the fluid moves from fluid flow direction is this against gravity. Okay, and normally rotometers are supposed to be kept vertical only. Otherwise, you have to do recalibration. It is inclined. Rotometers are kept vertically, and there is a float. It will be like an inverted cone. Okay, and cross section of the pipe keep on increasing. Mostly the rotometers will be transparent, that you will be able to see the pipe that's flowing because you want to see where the float is. So conical section means it will not go like this. A small increase in cross section area. That's all. Okay. So that cross section area, the pipe keep on flowing, and the principle is when the liquid flows upward, it offers a force on the bottom of the float, the top end. So float, the bottom side, it applies force, upward force, and there is a gravity because of its own weight. The gravity force pulls the float downwards. At some place, the upward force offered by the flow, downward force offered by the gravity, it equals. And if the flow rate is less, that balance, we normally take one point, either the lowermost point or this collar point or topmost point. Depending upon the manufacturer, we can change that. But it should be according to manufacturer's specification. He will tell you should take reading from bottom of the float, you take the reading, or in the top portion of the float you start taking reading. Because accordingly the scale will be fixed relative to that position. Only he knows. So he will indicate how you should take reading. I have taken this, the collar of the head. So now right now we are showing some part. Okay. So if the flow rate is slow, this float will come down and show a lower reading. If the flow rate is high, this balance, the equilibrium happens at a higher position. So you will be able to calibrate this height where the equilibrium takes place to proportional to the flow rate, and then directly take the reading of flow rate directly from the scale. You measure what is the centimeter. Proportional to that, there will be a table. Refer to the table and then find out what is the discharge. This is rotometer. Simple. There is nothing, no technology, nothing for this. Alright. Any questions? Nothing? Hot wire anemometer. Here you have to pay attention. Not as simple as this. Of course, not very rocket science, but there is something to understand. Okay, unless you listen, you will not be able to write on the exam by yourself. You have two wires, conducting wires. Here you will have a thin wire, which is you are not able to see. You are not able to see. When current flowing through a conductor, the conductor gets heated up. You are aware of it? After some time you touch the bulb, you feel hot, isn't it? The bulb is hot because already the filament through which the current is flowing is actually becoming hot. That hotness is due to radiation or conduction or convection. It transfers to the outer bulb and that bulb becomes hot. So when a current is flowing through a conductor, the conductor is becoming hot. Okay, and that wire between these two terminals. Of course, one terminal is here, another terminal is here, and these are all the ceramic tubings, and ceramic cement. Alternate layers will be there, just to separate them from one wire from other wire. No big purpose. It gives a structural rigidity. Also, it separates it out. Like in the high tension lines, they put one ceramic tube. Have you noticed it? One wire, one ceramic tube. They will tie it to another ceramic tube, another ceramic tube. This will be connected through a metallic strip. What is the purpose? No big purpose. I don't want the first line, second line to touch due to air or wind. I want them to be separated out. So I put one ceramic tube, and distant that, maybe here one ceramic tube, one wire will go. Here one ceramic tube, one wire will go. Here there will be a metallic strip to separate these two wires out. Metallic strip is a conductor. We don't want to put conductor directly there because that will conduct and short circuit. So put a ceramic tube there. They are also same purpose. They are all white and green or alternative ceramic tubes basically that separate two wires. That's all. Otherwise, no big function for that. You have two wires, and here is the hot wire. Now, how do we measure flow using this? Okay. Whatever I have shown you, I have zoomed down and then make it available here. That is actually a small element. Just for you to visualize, I have shown it as a big tube. Now it has gone to its place. Inside the pipe, we put that hot wire in. What is the working? Now you connect that two terminals to one arm of Wheatstone bridge. So fairly you should have some understanding about Wheatstone bridge because we have discussed enough prior to carry on. So initially, before fluid flow takes place, we switch on the Wheatstone bridge and the supply and all that. So there is a power supply through which the current goes, and some heating takes place, and the coil reaches some particular temperature. Coil reaches particular temperature. When temperature is high, the resistance of that material will be when temperature is high, the resistance of the conductor is high. Okay, high. Okay, so it has now reached some temperature, and it has reached a high temperature. Now, because of that, resistance is high. So what you do, you adjust your rheostat. This is a rheostat or a variable resistor. Other than that, 4 resistors which forms the Wheatstone bridge. Adjust that. This is for adjusting the current flowing through that, and this is for adjusting. These 3 resistors are adjusting for balancing the bridge. This is for adjusting the amount of current flowing through the conductor. Okay. There are 2 methods by which you can measure the flow rate. One is constant temperature method. I am explaining now constant temperature method. So initially no fluid is flowing. I kept the device inside, allowed the current to flow. It got heated up. Some high temperature. Accordingly, there is high temperature. Now what I do vary any one of this resistor or a combination of these resistors and balance the bridge. Now the bridge is balanced. No, I'm sorry. Constant temperature method, I will not touch the Wheatstone bridge. Yeah, initial setting, the sensor is kept inside, it's getting heated up at a hot temperature. I balance the bridge, and that is my initial condition. I'm right. Okay. So that's the initial condition. Now we allow the liquid to flow. After allowing the liquid to flow, I will not disturb the bridge resistance. That is what actually wanted to mean, but then got confused in it. So you have a Wheatstone bridge. Initial setup, wire is on, Wheatstone bridge is on, hot wire anemometer is hot. We allow sufficient time and wait for it. No liquid is flowing. That time the resistance of the hot wire anemometer will be high. It reaches its saturation temperature. Then you balance the bridge. Now galvanometer reads 0. After this is clear, right? Now balance the bridge, allow the liquid to flow. when allowing the liquid to flow, what happens? When liquid flows through the hot wire, the liquid carries the temperature and go, isn't it? Takes heat from the hot wire and then go. So what will happen to the temperature of the hot wire? After liquid is allowed to flow, it will decrease. Okay, it will decrease. In constant temperature method, you wait for some time, few seconds, typically 30 to 40 seconds or maybe 1 minute you wait. The temperature would have fallen down and resistance also would have fallen down. There will be an unbalanced voltage. There will be an unbalanced voltage. Okay. Now your real this starts. Here you have a meter which you know how much resistance you are increasing. You adjust this rheostat so that you allow more current to heat up the coil again. Whatever is the wire, you increase the current. Basically, heating is coming because of I square R losses. If the current increases, the heat will increase. I square R losses. So heat, as I heat, it goes up. So you increase the current that is flowing through this connector, and if current is increasing, temperature is increasing. Earlier, at some high temperature, we had the bridge was balanced. Now you bring back the bridge to balanced condition, not disturbing these three resistors, but just varying this rheostat. Allow more current and bring the bridge to balanced condition. How much of resistance you have reduced is a measure of the amount of flow. If the flow is slow, discharge is less, you need only little extra current to bring back to balanced condition. If the flow is high, you need to provide more current, more heating to bring back to the balanced condition. Our balanced condition is the high temperature level. Is the principle clear or any confusion? Not yet. It's clear? This is constant temperature method. That means reading is taken when the temperature is constant. Some temperature, naturally high temperature we set, same temperature we re-establish, then we take reading, then it is constant temperature. Then constant current method. Constant current method. In constant current method is much simpler. We put the we put this initial setting. Allow the don't allow the liquid to flow. A hot wire anemometer is inside, and you supply the current. The heat is there. Okay. Now if you increase, you balance this resistors and make it zero, allow the liquid to flow, there will be an unbalanced voltage, and proportional to that there will be a galvanometric reading, isn't it? At this time, whatever is the reading shown by the galvanometer, take that reading and then calibrate that in terms of measurement. Normally that is how we use the Wheatstone. That is the first method. That's a simple method. How do we do? We take galvanometer, do initial setting when fluid is not flowing. Bridge is balanced. Once bridge is balanced, allow the liquid to flow. Bridge will become unbalanced. Unbalanced means what? One resistance will vary, whether it will increase or decrease. In this case, the resistance will decrease. Why? We balance the bridge at high temperature, high resistance. When fluid is flowing, the temperature reduced, resistance reduced, so there is a reduction in the resistance, so you will get unbalanced. That unbalanced voltage is a measure of amount of flow. If the flow is less, the unbalanced voltage will be less. If discharge is more, the unbalanced voltage will be. So this method is one method, that's another method. This method is called constant current method. Why it is constant current method? Because we don't touch this rheostat at all. Rheostat is the one which allows the amount of current that is flowing from the battery source to the circuit. So this entire current flowing to the circuit is covered by this one rheostat. In the second method that we have discussed, we have not touched that current at all. Current is constant current that is flowing. So it is called constant current method. In the other case, we want to re-establish the equilibrium. For that, we vary the current, and the amount of current that we have varied becomes a measure of the what is that? I normally know we put an ammeter in the middle of the circuit, and the amount of current that we have increased from balanced condition to unbalanced condition becomes a measure of flow that is done. Any questions? All these devices. So today we have discussed about anemometer, rotometer, and with that I think your third unit comes through. Next class onwards we will be talking about just a few.